Okay, welcome to lecture 15 of the planets. And today, for the lecture, I'm going to ask you to fasten your seatbelts, put your tray table in the upright position, because we're going to be flying high and flying fast, and indeed skipping over some territory all the way up to chapter 14 to discuss our sun. And in fact, it's rather remarkable that we are waiting this long to discuss our sun, because when you think about our solar system, by far the dominant object in our solar system is the sun. In terms of mass, the sun is 1,000 times more massive than the largest planet, Jupiter. The sun obviously is the most luminous object, way more bright than any of the planets or anything else in our solar system. The sun is producing energy, as we'll discuss in great detail. And in fact, it's the energy angle on the sun that is something all of you owe your existences to. If you think about it for just a moment, almost all of the energy sources that we enjoy and indeed require to exist on the planet Earth, almost all of that energy ultimately comes from the sun. Now, that's a rather strong statement. Let's think about that for a minute. Most of the energy you need in your lives comes from the sun. Now, of course, it's obvious that solar energy, using photovoltaic cells, depend directly on sunlight that hit the photovoltaic cell and produce electricity. You all are comfortable with solar power as one of the viable solutions to our energy needs in the upcoming decades throughout your lifetime. But what about other energy sources that we depend on and require? For example, the fossil fuels, oil, natural gas, coal. Where is the sun in that equation? Well, all of the fossil fuels came from animals and plants that lived millions of years ago, died, decayed, got submerged under hundreds or thousands of feet of rock and dirt, and then we drill down to get the ooze of their remains, the oil, the gas, the coal. But if you think back to those animals and plants that died so that we could put it in our gasoline tank, those animals and plants, of course, depended on the sun for their energy. Plants directly, they do their photosynthesis by using solar energy. Plants are natural solar energy collectors. And animals eat plants, without which the animals couldn't survive. So the animals owe their existence ultimately to an energy source 93 million miles away, namely the sun. And you might say, well, okay, that's pretty impressive. The sun really is the origin of all of that energy. Fossil fuels, solar power. What about wind power? Suppose you're one of those people who correctly thinks that wind could provide some of our energy in the next decade or century. Well, wind, if you think about it, is powered by the sun. It's the solar energy hitting the earth, warming the air, causing the air to circulate. So there again, it's solar power. Literally the photons coming from the sun that power almost all of our lives. So today in lecture, I'm going to tell you a lot about our sun with a special emphasis on where does all of that energy come from in the sun. Now, we are skipping forward, as said, to fasten your seatbelt and put your tray table up, because we're launching ourselves over a few chapters that we will come back to. This week you should read chapter 14. It's very easy reading. You'll learn everything you ever needed to know about the sun in chapter 14. The homework assignment, of course, is also on the sun and also on chapter 14, and due, as usual, Friday at 6 p.m. So I really hope you enjoy reading the chapter. Find 2 or 3 hours. You will use the information you learn about our sun in lecture and by reading the chapter for the rest of your lives. Now, there's one other aspect of the sun which is partly why I launched forward to chapter 14. I've been looking forward to this for over a year. This lecture today and the lecture Thursday, I've been waiting for all of you to be in the audience, looking forward to giving these 2 lectures because of one remarkable fact, which is that the day after tomorrow, there will be a partial solar eclipse. Quite rare, and in fact, you're seeing just what it'll look like, we predict, in the very early moments of that eclipse. I'm going to get my laser pointer out. And so if you look carefully, the sun magnified will have a little bite taken out of it because the moon, as you all know, in its orbit around the Earth, the moon will be crossing between us and the sun. And so tomorrow, Thursday, day after tomorrow, between 2:30 and 4, just before class, I heartily invite all of you for a possibly once-in-a-lifetime opportunity. And that is to come out to the grass area right across from Pimentel, right out these doors, go straight a little bit to the right. There's a grassy knoll with a pond in the center. You all should have gotten an email about this. The grass area right across from Pimentel, a 1-minute walk from this hall. And between 2:30 and 4 on Thursday, we will have specialized glasses that allow you to look directly at the sun. And so that also is a once-in-a-lifetime opportunity. I'll say a little more about this partial eclipse at the end of today's lecture, but in case some of you have to leave, and I know there's always a handful that have obligations, so you have to leave, I wanted to let you know at the beginning of the lecture, and I'll remind you with more details at the end. Day after tomorrow, 2:30 to 4, get your little butt out to the grass area, and you will see something special. And it doesn't matter when you come between 2:30 and 4. The best is around 3:15. But if you come earlier, before 3:15, depending on which classes you have, that will be fine. Okay. Now I'm going to give a lightning lecture on the structure of our sun with a special eye toward the energy production, the prodigious energy production of our sun, with some other questions about our sun thrown in. So let me tell you what questions you may have about the sun. If you thought about it for 25 minutes, you would come up with lots of interesting questions about the sun, such as, what is our sun made of? What is the process by which the energy is produced in our sun? It's, of course, nuclear reactions, as all of you know, and we will be describing those nuclear reactions in the lecture today in great detail. If it's nuclear reactions, will the sun use up its fuel? Whatever is the input ingredients to the nuclear reaction, will we run out in a century, in 1,000 years, in 1,000,000 years? When will the sun die? Is the sun's light output constant? Is the luminosity of the sun constant? This bears on global warming. There are those people who think, oh, well, the sun is varying in brightness and that's the cause of global warming. Well, we'll discuss that, and I'll tell you that it's not the case. You might ask, If the sun is so massive, why doesn't it collapse under its own weight, under its own gravity? We'll discuss that. We'll discuss a little bit about how the sun formed in the first place. You already know a little bit about that. Toward the end of the lecture, I'm going to talk about something precious, namely sunspots. And the reason it's precious is that on Thursday, when you go to the grassy area and I give you the special solar glasses, you'll have an opportunity, maybe, if you're lucky, to see sunspots on the sun directly with your naked eye. So that will be nice. And I'll try to give you a heads up about the nature of sunspots. Why are there dark spots on the sun at all? And what's this deal of a sunspot cycle that you might have heard about? And then finally, we're going to talk about the structure of our sun, the layers, the interior layers of our sun that in some ways resemble the Earth, with different regions that are distinctly different, just as the Earth has a core and a mantle. Okay, now I'm going to answer some of these questions right now as a sort of preamble to today's lecture. What produces the enormous amount of light energy? Nuclear reactions. In brief, 4 hydrogen atoms in the center of the sun combine into 1 helium atom. 4 hydrogens into 1 helium. That's called fusion, and I'll describe that in detail. How many years will the sun keep doing this? Well, lucky for us, some 5 billion years. You don't need to sell your stock investments. Is the sun's light output constant? It's constant, within 0.1%. 1 part in 1,000, the sun stays the same brightness. Why doesn't the sun contract due to its own gravity? Pressure. Same reason that the Earth's atmosphere doesn't collapse, the Earth's interior doesn't collapse. The sun is also held up against its own gravity by pressure. And we'll talk about that. We'll talk a little about how the sun forms. Of course, you already know there are giant clouds of gas and dust floating around our Milky Way galaxy, and within those clumps of gas and dust, occasionally gravity takes over and the gas and dust collapses under its own weight, every atom gravitationally attracted to every other atom, and they begin collapsing down into a denser and denser clump, which becomes a star. And then what are sunspots? They are cool regions on the surface of the sun. They're dark, and they're dark because they're cool, and they're cool because of magnetic fields piercing the surface of the sun. Okay, I've just given you a review of today's lecture, or a look in advance. Now let's go full speed ahead. First, some properties of our sun. In brief, it's enormous and massive. You all know that. It's about 93 million miles away from the Earth, 1.5 times 10 to the 8 kilometers, the distance we've been calling 1 AU all semester long. The mass of our sun, 300,000 times more massive than the Earth. The Earth is a speck of dust compared to the sun, and you live your whole life on that speck of dust. The size of the sun, over 100 times the diameter of the Earth. The density of the sun, this is a shocker. The density of the sun is only 1.4 grams per cubic centimeter. 1.4 grams per cubic centimeter. What does that mean? Well, when you took high school chemistry, you may remember your high school chemistry teacher saying that the density of water is 1 gram per cubic centimeter. So the density of the sun is the same as the density of a cup of water. Amazing. And that gives you a clue as to the internal composition of the sun. Only an object that was liquid or maybe compressed gas could have a density no greater or hardly greater than that of water. So those are the basics of the sun, but the most precious property of the sun that we've talked about already is its energy production, and the energy it produces is about 4 times 10 to the 26 watts. 4 times 10 to the 26 watts. Remember, a light bulb, a typical light bulb in your bedroom or a living room is 100 watts, 10 to the 2 watts. The sun is way, way brighter than a 100-watt light bulb by a factor of 10 to the 24. So the sun is producing an amount of energy that is virtually inconceivable. So let's do a quiz. I've got a bunch of them scattered throughout today's lecture. They're mostly pretty easy, but one or two are a little bit challenging. Here's the first quiz question. Suppose every person on the planet Earth, on average, every human being uses about 1,000 watts. Why do I say 1,000 watts? Well, one light bulb is 100 watts. And I think typically in our lives, whether it's your laptop that's open or you're microwaving something in the oven or you're turning on some electrical device, that's another 50 watts or 100 watts or 5 watts. Roughly speaking, when you turn on an electrical device, you're using electricity at about the same rate as a light bulb, roughly. So 100 watts times 10 electrical things you have on at any time. Your refrigerator is on even when you're sleeping. It brings your total budget of energy to about 1,000 watts. You're using 1,000 watts every second of your life. And the question is, how much energy per second do humans use in the entire world? Adding up all the energy usage of all the humans, how much do we humans as a species, how much energy do we use? Here are your answers, possibly 7 times 10 to the 8, 7 times 10 to the 12, 7 times 10 to the 16, and 7 times 10 to the 20. You're only going to be able to estimate this answer, but let me give you 20 seconds to think about the answer. How much energy does humanity use per second? Okay, let me see your answers. I'll tell you what I see. I see lots of B's, some green iPhones, some green iPads, blues, some yellows, a few yellows. I would say half of the people have greens, maybe more than half. Well, here's the way I would do this problem, and you can do it in your head. 1,000 watts per person, you need to know how many people there are populating the planet Earth. And of course, we all know that there's roughly 7 billion people on the planet Earth right now. 7 billion you can write in exponential notation as 7 times 10 to the 9, that's a billion. So if you multiply 7 billion by 1,000 watts, 10 to the 9 times 10 to the 3 is 10 to the 12. So I think the right answer is 10 to the 12 watts. Okay? The reason I put this question up is twofold. One is that you can estimate something amazing like how much energy does humanity use just in your head. That's kind of amazing. The other is how much energy is this compared to the energy production of the sun? Well, remember the sun, what was the energy production of the sun? 10 to the 26 watts. 3.8 times 10 to the 26 watts. And in comparison, we humans are only using 10 to the 12. So the sun is producing way more energy than we humans need by a factor of 10 to the 14 or so. So if we could harness the power of the sun, we would solve all of our energy troubles easily. Okay, so that's the backdrop to solar energy. Here's another question. Ready for this one? How much energy in joules do all humans use in 1 year? How much energy in joules do all humans use in 1 year? 10 to the 8, 10 to the 12, 10 to the 16, 10 to the 20. How much energy do we use in a year? I'll give you 20 seconds to think about this one. This is a little harder. Well, this is a hard problem. Let me see your answers, but then we'll work it out, of course. I see D's. I see C's. I see people waving their piece of paper to get cool. You have a question? Yeah. Yeah, we're going to get to that. We have somebody very disgruntled. I promise to make you happy. Yeah, there's some problems here. Let's work this out. By the way, we already worked out the answer to how much energy a human being uses. But in a year, remember that watts represents energy usage per second, joules per second in particular. And so if we want to know how much energy we use in a year, you have to multiply by how many seconds go by in a year. Anybody know how many seconds there are in a year? Anyone? 30? 36,000? Yeah, well, 60 seconds in a minute and 60 minutes in an hour. So there's 3,600 seconds in an hour. But then we need to know how many hours there are in a year, and this is getting kind of boring. Anyone know how many seconds in a year? Don't look it up online. It's what? Yeah, it's pi times 10 to the 7. She just said 31 million. I converted that in my head to 3.1 times 10 to the 7. Fair? And a good way to remember it is pi times 10 to the 7. I'm speaking a little bit humorously, but you can always remember how many seconds in a year. 3 times 10 to the 7, pi times 10 to the 7. So let's use that. 7 times 10 to the 12 watts was the answer to the last question. 1 year is how many seconds? Pi times 10 to the 7th. Okay, let's just make it easy on ourselves. 3 times 10 to the 7 seconds in a year. Multiply the wattage by the seconds. He's still unhappy back there, by the way. I just want to make everybody clear. He's still not happy about that W. And so if you multiply the two, 7 times 10 to the 12 watts times 3 times 10 to the 7 seconds, that looks like 10 to the 19, adding that exponent to that exponent. And then there's 21. So it looks like it is indeed answer D, except for one problem. What about that W? The answer here is in joules. It even says that in the question. All of my answers are wrong because I have the wrong units. The units of energy should be joules, not watts, which is a unit of energy usage per second. So we need to get rid of that W. See, I was ahead of you. And convert them to joules. Bad, good, bad, good, bad, good. And this is just to remind you that watts represent energy usage per second, and joules is actually energy. So to summarize, the sun has a density similar to that of water. It's very massive. And the water aspect proves to you that the sun must be made of material that is hardly more dense than water. That means compressed gas. If you take a gas and you compress it with its own self-gravity of the sun, that gas will compress down to the density of roughly water. There is, of course, no hard surface on the sun. You can't take a spaceship to the sun and walk on the surface. It's just made of gas. And of course, you would probably add you cannot take a spaceship to the sun, because if you did, the spacecraft, as it got closer and closer to the sun, would melt, unless you're clever and go at night. Now, how do you know what the sun is made of? Well, of course, you take a spectrum. You spread the white light from the sun out into all of its wavelengths or frequencies, from blue through red, and lo and behold, when you do that with your diffraction grating, you see all the colors of the rainbow. Why? The sun is hot, and it's emitting thermally. Thermal emission from the hot sun gives you the full spectrum of colors, but certain wavelengths are missing. And you can see it by looking at that spectrum pretty clearly. Certain wavelengths are simply missing, and they correspond, as you know, to wavelengths at which atoms in the atmosphere of the sun are absorbing the light at those specific wavelengths, trying to get out. Light is trying to get out of the sun, but the atmosphere of the sun, the so-called photosphere, those atoms absorb light at specific wavelengths due, you know, to the energy levels within the atoms, the specific energy differences in the atoms that you all learned about weeks ago. So we can learn what the atoms are in the sun. You look over at the periodic table over here, and you ask, is there hydrogen? Is there helium, carbon, boron, nickel, iron, calcium? Sure enough, there are absorption lines from all of the elements in the periodic table, all the naturally occurring elements up to uranium are there in the sun, all of them. And in fact, you can do an analysis to figure out how much of each of those atoms is in the sun. The dominant atom of the sun, hydrogen, 70-some-odd%. Helium is the next most popular atom in the sun. And then there are small amounts of everything else. In other words, the sun is made 98% of the simplest atom, hydrogen, and the next simplest atom, helium, and then small amounts of all the other elements in the periodic table. And they're all producing absorption lines, spectral lines, so you can measure how much of each of those elements is there. And it turns out that when we analyze other stars, something we're not talking about in this course, when you analyze the chemical composition of other stars in the night sky, it's the same. Other stars at night, by and large, have the same relative composition. Mostly hydrogen, some fair amount of helium, and then small amounts of carbon, nitrogen, oxygen, phosphorus, iron, nickel, and so on. Okay, what about this question of what holds up the sun against its own self-gravity, this massive object, 300,000 times the mass of the Earth? How does it hold itself up against gravity? Well, you know the answer. Gas pressure balances the gravity. So in a graphical form, gravity is shown in green. Gravity pulls every atom of the sun toward the center. But the gas pressure, the collisions of the atoms as they jostle around, remember we talked about this, pushes back. And so a star like our sun will contract due to gravity, making the density of the sun higher and higher and higher until the density gets so high that pressure balances gravity. And so the sun holds itself up by its own pressure, and the pressure has to be huge because the pressure has to support the weight of all of the mass of the sun above that level. So the pressure at the center of the sun must be enormous, because the pressure here has to cause a force that pushes back equal to the weight of all of the material outside the core. Pressure balances gravity. And indeed, you can write a computer program to calculate how high the pressure is, how high the density is, how high the temperature is in the center of the sun and throughout the interior of the sun. And the answer is, in the center of the sun, 15 million degrees Kelvin. Hotter than you can even imagine. And of course, you remember what temperature means. It means that the atoms are moving extremely fast. That's what temperature means, that the atoms are moving around incredibly quickly, corresponding to that temperature. And what that means is that the collisions between the atoms are very violent. When two atoms run into each other, moving at that high speed, at 15 million degrees Kelvin, the collisions are catastrophic. They're absolutely stupendous collisions. And indeed, the temperature is so high that the nuclei of the atoms collide. The electrons buzzing around outside, if any, don't matter. They're just so light, they don't make any difference. Nuclei, the centers of the atoms, can literally collide and engage in nuclear reactions. This never happens on the Earth. Here in the Earth, at normal room temperature, even in the center of the Earth, the temperatures are not high enough to bring the nuclei close together. And I'll tell you about that right now. Why don't nuclear reactions occur on the Earth? And why is it that they can occur on the sun? The answer is simple. The nucleus of an atom is positively charged, right? The nucleus of an atom has protons and some neutrons, and therefore is positively charged. And if you try to slam one proton against another proton, or a set of protons in the nucleus against another set of protons, you all learned in high school physics that like charges repel each other. Two positive charges will repel, so you can't get nuclear reactions in the in the Earth, because those positive charges repel each other. On the Earth, the temperatures are too low, and therefore the speeds of the atoms are too low to bring the two nuclei close enough to react. But in the sun, the temperatures are so high that if two nuclei, positively charged, are aimed at each other by chance, they will touch and react in nuclear reactions. So only at temperatures of 10 or 15 million degrees can you get two nuclei to get close enough to react, fighting off the electric repulsion of like positively charges. Okay? And these words say exactly what I was saying. When the nuclei touch, then a nuclear force takes over. And now, for the next 10 minutes, I'm going to enter into a new microscopic sub-nanometer realm. We're going to talk about subatomic particles that engage in nuclear reactions in the sun. And the first thing we're going to talk about are neutrons. You'll see that they play a role. A neutron is an elementary particle that lives typically in the nucleus of an atom. And as their name implies, they are neutral in charge. Of course, you can tell that the particle is neutral in charge by the name, which reminds me of a joke. All right, if you insist. So this neutron walks into a bar. Bartender, how much for your best beer? Bartender says, for you, no charge. Next slide, please. Neutrons, it turns out, are not stable. They decay naturally into a proton, an electron, and a neutrino. I'll talk about neutrinos in a moment. Notice this interesting nuclear reaction, a neutron transmuting itself into a proton and electron. Notice something beautiful here. Charge is conserved. You started off with no charge. A proton and an electron have opposite charges that cancel. In any nuclear reaction, charge must be conserved. And as I'll mention in a moment, mass and energy together have to be conserved as well. There are, in fact, other quantum mechanical properties that have to be conserved, which I'm not going to talk about right now. This process is important. It has a name. It's called beta decay. Don't worry about it, but just keep in mind that a neutron can easily change itself into a proton plus an electron plus a neutrino. The neutrino, by the way, as you can imagine, has no charge as well from the name neutrino. And again, I'll talk about it in a moment. Similarly, a proton, which I've made explicitly positively charged, a proton can decay into a neutron plus a positively charged electron called a positron plus a neutrino. Is charge conserved in this reaction? Yeah. Proton's positively charged, neutron has no charge, but this positively charged electron, the positron, does have positive charge, so charge is conserved. So particles can change from one to the other as long as they conserve charge and mass energy and some other properties. Now, what about this neutrino deal? Well, a neutrino is a particle, but ephemeral. It is very low mass. In fact, nobody knows exactly what the mass of a neutrino is. It's very tiny. It travels at nearly the speed of light. And so neutrinos are particles that particle physicists study. You can get your PhD studying the neutrino. And they play a role, obviously, in these simple nuclear reactions. Now, this is just a warm-up. Do you have a question?
Yeah, what's the line above the first neutrino?
Oh, yeah, thank you. So there's a neutrino with a little line, and here's a neutrino without a line. There are neutrinos in this universe, and there are anti-neutrinos. The line says it's an anti-neutrino. And that's because of something called lepton number that's conserved. But we won't talk about that. Okay. I've just shown you two warm-up nuclear reactions. Now let's get to the juicy part, how the sun engages in nuclear reactions, powering itself, generating this 10 to the 26 watts that we all dearly depend on. I am going to show a slide now. I'm preparing you psychologically for a pretty complex slide that has the details of the chain of nuclear reactions that are taking place in the sun every second of your life. Are you ready? You start with two protons. One proton collides with another proton in this energy generation process in the sun. And when they collide, something remarkable happens. They stick, and one of the protons converts itself into a neutron by the process I just showed you. Proton converted itself into a neutron. They stick together. Obviously, the proton turns into a neutron plus the positron that you know about and the neutrino that you know about. Now you have a new atomic nucleus. It's hydrogen because it's got one single proton, as all good self-respecting hydrogen atoms have, one proton. But now there's a neutron stuck there. This is heavy hydrogen. You would call it deuterium maybe, but it's an isotope of hydrogen. Okay, first step. Ready? This positron does something amazing. It is, of course, electrically attracted to negatively charged electrons, this one being positively charged. So as soon as this positron is out running around town, it runs into a delicious electron that's negatively charged. They are, of course, attracted to each other, and they actually react. And when a positron and an electron react, their mass is utterly destroyed. They annihilate each other and convert their mass into energy in the form of light. Indeed, high energy light, high frequency light, called a gamma ray. And in fact, they produce two of them. So whenever this positron is produced in this reaction, something wonderful happens. The positron reacts with the electron. They themselves produce energy, light energy, that eventually worms its way out of the sun. So keep in mind that you're seeing now step one of a network of nuclear reactions, the first of which right here produces light, high energy light called gamma rays. Okay, that's the first step in the chain. Hang on to your hats. This heavy hydrogen then reacts with another proton. Heavy hydrogen, deuterium in other words, plus a proton, they stick together, and now you have two protons and a neutron. They're so tightly bound that they actually have negative energy, and they spit off another gamma ray, more light energy. So you get even more energy from this reaction. Now keep in mind, this collection of two protons and a neutron has a different name. Why? Because the definition of helium is any atom that has a nucleus with two protons. You see the two there. By definition, helium is simply an atom whose nucleus has two protons, no matter how many neutrons there are. In this case, only one. So this is helium, but it's missing its normal second neutron. Nonetheless, it's helium, helium-3, you would call it. And again, the important detail is, in the creation of this helium, yet another gamma ray, light wave, was given off with high energy that can warm up, power the sun. The last step in the nuclear reaction chain is that one of these helium nuclei reacts with yet another one. Two protons and a neutron, two protons and a neutron. They collide, they stick, and remarkably, two protons are ejected, and you're left, if you do the math, you're left with two protons and two neutrons. Look at that thing right there. That's a helium nucleus, a normal helium nucleus with two protons and two neutrons. And if you look over at the periodic chart, yeah, helium is supposed to have two protons, but the atomic weight is 4 right there, if you can see it. 4 meaning two protons and two neutrons. So here we have normal, self-respecting American helium right there. And so if you do the math and take a deep breath and look at what happened in this nuclear reaction chain in the sun, in the end, the net result, 4 protons came together, some of them converted into neutrons, producing helium. Here it is again, 4 protons created helium, and gamma rays were given off, which of course have energy. Remember that Planck's constant, h times the frequency of the light, h times f, is the energy of each of those photons. So we got tons of energy, and hydrogen was converted into helium. Every second of your life, the sun in its center is doing this nuclear reaction in uncountable numbers. Huge numbers of hydrogen atoms are being converted into helium atoms. And so the summary is 6 hydrogens went in. You had to add 2 electrons. Remember the electrons. And what came out was helium and 2 more protons, 2 hydrogens. So a couple of neutrinos, they don't react with anything, so forget the neutrinos for the moment. And then these 4 gamma rays. So energy was produced in this nuclear reaction. Okay? That's it. There are some other nuclear reactions that occur in the sun, but this is the main one. By the way, do I expect you to remember this? Actually, no. I can't even remember this myself. But you get the idea. Protons combining with protons, eventually forming helium. Here's a quiz question. Just to, again, keep you tuned up. Which particle has the greatest mass among all of these? Helium, electrons, protons, or deuterium? You can answer right away. Which of the 4 has the largest mass? Guesses? Well, the answer is, of course, helium, because it has 2 protons and 2 neutrons, so they blow away electrons and protons. And deuterium, as I mentioned in passing, is simply hydrogen with an extra neutron. So helium is more massive. Okay, let me show you these nuclear reactions in action in an animated video. Here's step 1, proton plus proton. Are you ready? Go. Boom. The reaction occurred quickly. I'll do it again. 1 proton plus 1 proton combine into a proton that sticks to the other one, but it gets converted to a neutron. Ready? Here we go. One more time. Proton plus proton gives you proton and a neutron stuck together. Next step, remember that resulting nucleus, a proton and a neutron that we call deuterium, reacts with a proton. Here's that reaction. Watch carefully. You'll see a deuterium nucleus, proton and neutron, hit a proton. Oops. Hang on. There. Ready? Here we go. I'll try it again. There. Here we go again. Deuterium plus proton. See that little yellow thing that came off? That yellow ball represents the gamma ray, the photon, that carries away energy. And then finally, the last step in the chain, a helium-3 nucleus hits another helium-3 nucleus, reacts to form normal helium-4. Here we go. Cool. Here's another one. And you notice the 2 protons go off as advertised. So here you see the helium nucleus fully formed out of the nuclear reaction. Here's a cartoon that shows the same thing again. Let's not walk through it. But you see proton plus proton. They collide. They produce deuterium. Plus a proton gives you helium isotope. And then that helium isotope reacts with another helium isotope to give you normal helium-4. Here's a quiz. One more quick quiz. What's that thing? Is that thing there deuterium, tritium, helium, or heavy hydrogen? Hydrogen-2. What is this thing here? You can show me your answers. I see C, I see B, I see D, and I see people folding the paper, putting it in their pocket. So, this thing has 2 protons in it, and again, by definition, any nucleus that has 2 protons is helium. So this actually is helium, albeit helium with just 3 nuclei, that is to say, helium-3. Now, one thing I've glossed over, and I apologize, is I have not told you where the energy comes from. these photons, these gamma rays fly off, powering the sun, powering life here on the earth. Where does that energy come from that is in the form of gamma rays? Well, you can get a clue if you do the math on mass, the mass of the particles. Remember that what goes in are 4 protons and 2 electrons into the nuclear reaction. What comes out is a helium nucleus, which itself has 2 protons and 2 neutrons. You can look up online the mass of a proton, multiply by 4, look up the mass of electrons, multiply by 2, add them up, and you get the mass of the input to the nuclear reaction, and do the same thing for the output. Look up online the mass of a helium atom. You can do that, and when you look up those masses, you find something wacky. And what's wacky is that the total mass that goes into the reaction is greater than the total mass that comes out. Mass in does not equal mass out. By a long ways, almost 1%. Mass is not conserved. And in fact, as you see here, the mass input is 0.007 greater than the mass that comes out. Almost 1% greater. File that away for your next cocktail party when you're talking to people about where energy comes from in the sun. 4 hydrogens combine into helium, but 1%, almost 1% of the mass is lost, gone. And you might ask, where did that mass go? Well, you kind of have a hint as to the answer. Mass can be converted into energy. And the missing mass, the fact that there's mass that was there originally and then is not there at the end, tells you something profound, especially when combined with the fact that what does come out of those reactions is the gamma ray photons that have energy. And of course, the answer to this puzzle is that the mass was converted into energy by the famous equation E equals mc squared. The mass that's lost was converted into energy, and c is the speed of light, as always. 3 times 10 to the 8 meters a second. You can see how enormously powerful this equation is and the consequences of this equation, because you take a relatively small amount of mass, but you get to multiply it by the speed of light, which is fast, squared, and that gives you a lot of energy for a small amount of mass. So E equals mc squared explains what happened to the missing mass in that nuclear reaction. It was literally converted into energy in the form of those gamma rays. Let me mention parenthetically, I won't go into it, that nuclear reactors on the Earth are also a source of energy for all of you to think about during the upcoming decade and during your lifetimes. I didn't mention nuclear reactors when I listed sources of energy that we may make use of in our energy needs in the future, but that was only for one reason, that nuclear reactors do not depend on the sun. The nuclear reactors that we use on the Earth to produce energy involve a different process that takes advantage of uranium, and uranium atoms are actually split in half, and energy comes out when you split uranium into pieces. So that doesn't involve the sun in any direct way. Nonetheless, let me offer you an editorial that there will be a serious question this year, this coming 5 and 10 years, a serious question as to whether or not we humans should be building more nuclear reactors to meet our energy needs. And it's controversial. Why? Because nuclear reactors have a little bit of danger. If you don't engineer them right, you could end up with nuclear waste, nuclear pollution. That's bad. On the positive side, nuclear reactors do not produce carbon dioxide as a byproduct, unlike the burning of fossil fuels. So nuclear reactors do not contribute to global warming and global climate change. They don't enhance the greenhouse effect. So you can see there's a trade with regard to nuclear reactors on the Earth and our use of them, a trade which, in my opinion, is not obvious. I don't come down strongly either way. I worry a little that nuclear reactors must be safe, but on the other hand, I'm delighted that they don't add to the global climate warming. So you'll all have to wrestle with these issues in the upcoming years. I promise you, nuclear reactors will come back as a prospective energy source as they are in Europe. Europe depends much more heavily on nuclear reactors than we do in the United States. Okay. One other aspect of the nuclear engine that is absolutely intriguing and beautiful, and that is that the sun has its own thermostat. How does the sun regulate its temperature, especially that 15 million degree furnace at the center? Well, you can do a thought experiment, and I invite all of you to do this thought experiment. Suppose the sun, by whatever reason, heated up a little bit more than the average. The temperature in the center of the sun goes up from 15 million degrees to 15.00001 degrees, a tiny increase in the temperature of the sun. Well, if that happened, here is the consequence. That higher temperature means, of course, that the atoms are moving faster. That's what you mean by higher temperature. And if the atoms move faster, the nuclear reactions will proceed more quickly. The number of nuclear reactions per second will go up because the atoms are moving faster and colliding more frequently with each other. When that happens, more energy is produced by those nuclear reactions, and the greater energy production means that the sun will have slightly higher temperature than it had before, and the higher temperature will cause the gas to expand. You all know that gas expands when it gets hot. And if the center of the sun expands due to that higher temperature, that means the density must therefore go down. The balloon of gas at the center of the sun just expanded to get bigger, and now the density inside that balloon is lower. What does that mean, that the density is lower? Well, it means that the atoms are farther apart now than they were due to that expansion. And if atoms are farther apart, they will collide less frequently. So this expansion and the increasing distance between the atoms causes the nuclear reaction rate to decline back toward what the original nuclear reaction rate was. The bottom line is, this is an amazing self-regulating system. If it were not so, the sun would have either exploded like a nuclear bomb, or it would have somehow contracted, shrunk down to a black hole. Instead, the sun is regulating its own temperature. If it gets too hot, the nuclear reaction rates cause more energy and it expands, and that expansion brings the nuclear reaction rate back down. So there is a natural regulatory system, which is wonderful, and it's why the luminosity of the sun is in fact constant, or nearly constant, over the hundreds and thousands of years. The sun's energy output has remained stable, indeed, for millions of years because of this thermostat-like process. Now, what I just said is not quite true if you look back several billion years. Over the last few billion years, the sun has become more luminous, about 30% more luminous. And the reason is that the sun itself is changing. Why? How is the sun changing? Well, remember, the hydrogen atoms are being converted into helium atoms. So the actual composition, the atomic composition of the center of the sun is becoming more helium-rich and hydrogen-poor. The hydrogen is being used up. Slowly but surely, we're burning the hydrogen fuel in the center of the sun, and someday the sun is going to run out of hydrogen. And as I mentioned at the very beginning of the lecture, we don't run out for another 5 billion years. But we will run out someday. And as the sun changes its structure, its luminosity slowly increases, which is sort of ironic. The nuclear fusion rate increases, new equilibria are achieved, and the sun gets a little more luminous over the course of 1 billion years. So the computer models show that the sun is about 30% brighter than it was 4 billion years ago. So you can see the wattage today is not quite what it was in the past. Now let me talk a little bit about the core of the sun. I've said that it was 15 million degrees. It's the inner 25% or so of the sun. It's where all the nuclear reactions occur. Why? Well, the nuclear reactions are going to predominantly occur where the temperature is highest, so that the collisions can occur frequently, and the two positively charged nuclei can hit. Then there are zones outside the core where energy is transported from the core to the surface of the sun. Somehow, those gamma rays with their energy have to make it out to get out of the center of the sun, transporting the energy to the outer region. And let me now walk you through the outer half of the sun. There are two regions that you should try to remember. There's the radiation zone. What does that mean? Radiation means the energy is carried by photons. Photons carry the energy from the hot center to the cool surface. And then just beyond that is a zone called the convection zone, where the energy is carried by convection. So there's an inner radiative zone and an outer convection zone, and they both carry energy. There's a boundary, of course, between them. Let me show you a picture now of what the sun looks like in the interior. Suppose you could slice open the sun with a knife, a big knife, and here's what you'd see. The sun has a core. There was an eclipse of the sun. The sun has a core. There's the radiative zone, the convective zone, and then the surface. Here they are again. The core is right there in the center where the nuclear reactions occur. Then there's a radiative zone where the photons carry the hot energy outward. Then there's a convection zone where the hot gas rises. You've already heard about convection with regard to the Earth. And then finally, there's the atmosphere of the sun, called the photosphere. Why do we call it the photosphere, the outer surface of the sun? Because when you take a photograph of the sun, or you use your eyeball, that's all you see, is the outer surface. So we call it the photosphere. And then there's hot gas around the sun called the corona, which we will talk about another time. Let me offer you a sense as to how photons do their work. A candle is a good example. When you have a candle, photons are carrying the energy away from the flame. So obviously, energy can be carried from a hot region, the flame, to the cooler outskirts by simply letting photons carry the energy. Now, one thing about photons is that a photon in the center of the sun has no clue where the surface of the sun is. Photons don't know which direction to go. Photons have no brains. You might not have known that, but they don't have any brains. So they wander aimlessly. And a typical path of a photon is shown by this random walk. The photons scatter off of atoms, scatter off of electrons, and so an atom goes one way and then scattered another way and then scattered another way, eventually making itself out to the surface by sheer luck. It's very much like a drunk person at 2 a.m. having drunk too much in the bar. They are on one side of the street. The drunk person wants to go to the other side of the street, but they have no idea how to get there. And eventually, by sheer luck, the drunk person will make it across the street. And so it is with photons. They eventually worm their way out and make it out of the star. In the case of our sun, it takes about 10 million years for the energy of a photon to finally get out. So it's rather interesting that it's sort of blind, dumb luck that allows the energy carried by photons in the radiation zone to make it out by this random walk process. Okay, and I mentioned it's slow. It takes over 1 million years for the photons to get out. Now, in addition, there's the outskirts of the convection zone. So there's the radiative zone, but then there is this convective zone. You already know about convection. The idea is that when there's a hot lower layer, hot gas rises and carries the energy with it. So going back to our flame analogy, a flame will heat up the air nearby and cause the hot gas to rise, carrying that thermal energy with it. So in the convective zone of the sun, energy is carried by hot gas rising, convection, just the same way it does in the mantle of the planet Earth, those plumes that carry hot rock from the center of the Earth upward. You can prove the convection on the sun by simply taking a picture. When you take a picture of the surface of the sun, it has that mottled appearance to it. You can see that hot gas is rising, causing hot spots like here and here and here and here. That's where hot gas is rising, carrying the heat. The bottom of the convection zone, of course, is heated by those gamma ray photons. And then, of course, cool gas in between the hot regions sinks down back to the center of the sun. So you have hot gas rising, bringing the heat with it, and cool gas falling. And that's a different energy transport mechanism than the photons, which was a separate way entirely. Now, there's a great deal of evidence of this convection beneath the surface of the sun, and there's no better evidence than a movie of the surface of the sun. Check out this movie. This is what the surface of the sun looks like. You're seeing time go by, minutes are going by. The roiling, broiling, turbulent rise of hot gases bringing energy with it, and the falling back in the cooler regions. I'll show this again. I love this movie. You can just sense the hot gases rising. This is just what it looks like when you go to a Japanese restaurant and order miso soup. If you watch for about a half a minute, you'll see the hot soup rising, and it looks just like this. Now, there's one aspect of that picture that you noticed, and that is this dark spot. That is a sunspot, and I want to spend the last couple of minutes talking a little bit about sunspots. Whenever you take a picture of the sun or even look with your naked eye, you might be lucky and catch these dark spots that sit there. They are regions on the surface of the sun that are cool, and because they're cool, the amount of thermal emission from them is less. Sunspots are simply cool regions on the surface of the sun. And whenever you take a picture of the sun, you might again be lucky to see such spots. On Thursday, day after tomorrow, when we look at the sun hoping to see this predicted, supposed partial eclipse of the sun, we may be lucky and get to see sunspots as well. Sunspots are not always there, but when they are on the sun, they're really quite remarkable, and you can see big ones with your naked eye, looking directly at the sun. The ultimate cause of the sunspots, why is the surface cool? It's because of the magnetic field. They come and go, the sunspots do, and they're due to magnetic fields that pierce the surface of the sun. And a magnetic field, when it threads through, penetrates the surface of the sun, it reduces the convective heating of that gas. The gas streams along the magnetic field and fails to heat the atmosphere of the sun. So whenever you see a sunspot, you're actually seeing not just a cool region, but a region that's cool on the surface due to the magnetic field that prevented the heating of that surface. So let's just hope on Thursday out there on the grassy area, and remember it's an hour and a half before class, let's hope that we get to see one of these gorgeous sunspots. You won't see it in such glory, but we will hope to see at least the dots. I'll tell you about the 11-year cycle next lecture, but let me just finish by saying that, if I can get there, reminder, next Thursday, 2 days from now, between 2:30 and 4, meet on the grass area and hope that it's not cloudy. See you out there Thursday afternoon.